Hello, welcome to this lecture. As I indicated in the last lecture that today we will start different properties of multiple random variables. Particularly this terminology might be we came across earlier also in the context of the single random variable. Now as in this module we are discussing the multiple random variable, we will just discuss the properties of this multiple random variable in the context of the multiple random variables. For example, that moments that we have seen that in the context of the area with respect to the origin, so far as the single random variable is concerned, that we have seen earlier. So here now basically we are extending those ideas to the more than one random variables, where to start with, as I am always doing that for the bivariate random variable case, and similarly the same concept can be extended to the more than two random variables as well. So we will be going through one after another their properties, that moments, then we will know. So moments, one part will be that expectation, where the expected values of different random variable associated with the in the multiple random variable will be considered. Then the covariance means how the random variables are covary with each other, and from that it will be taken to a measure of linear association, which is known as correlation coefficient, that we will discuss, and gradually we will move through the conditional mean, conditional variance, and then moment generating functions. Maybe we will see we may cover the moment covariance and correlation coefficient in this lecture, and gradually we will continue to the next lecture for the other properties of random variables. So to start with, in the general discussion of these properties of multiple random variable, as I was telling, that the same concept what we discussed earlier for the single random variable will be used here also. Only thing that dimension depending on the number of variable associated will be increased, and for that one there may be some more properties, some more measures will be considered to describe their association with each other. So the fundamental properties and the measures discussed before for the random variables are applicable for the case of multiple random variable also. Some additional properties and measures are introduced here to describe their joint variability, as I was telling that it may be linear or non-linear. Particularly when we are talking about the correlation coefficient, it is a linear association. The joint variability of the two or more components of a multiple random variables will be discussed. The properties are determined using the concept of the expectation, the expected value that we discussed earlier in the context of the single random variable. Here we will discuss with respect to the first, we will just take that same concept with respect to the two random variables, that is bivariate case, and same thing will be again extended to that more than two random variables. And in this discussion we will follow these notations, where the expectation, that is expected value of the random variable x is denoted by mu x, and expected value of y is denoted by mu y. Variance of x is sigma x square, and variance of y is sigma y square. So these are all in case of, we discussed earlier in case of single random variable, and if you quickly recall that this expectation of x is that x multiplied by that its density. That is, when we are talking about this expectation of x, that is, it is that over the entire support the integration for this x, this multiplied by that its probability density, and this integration will give you that expectation of this x. And when we are talking about the variance of x, and we are generally considering its second moment with respect to its mean. So So, when we are talking that second moment with respect to the mean, we are doing the integration after with respect to its mean, that is expected value. Now, we have denoted this one as your mu x. So, this is your mu x, this square, then that probability density. This integration will give you that variance of x. So, these are for the single random variable. So, these notations we are just using. So, this is noted as the sigma x square, and similarly for the variable y. Particularly two variables is considered in this bivariate case, and that will be seen here with this notation. So, expectation of x is mu x, expectation of y is mu y, variance is sigma x square, and variance y is sigma y square. Now, the expectation operator or the moments introduced in the earlier lectures for a single variable can be extended to two or more variables, and two different cases as also discussed in case of this single random variable is that one is the discrete case and another one is the continuous case. So, discrete case means when both the random variables considered is discrete random variable, and continuous means when we are considering it to be the continuous, both the random variables are continuous. So, two different cases will be considered, and so first we will take off this discrete case. So, in general when we talk that here that r comma sth joint moment. So, now remember that in the single random variable when we discuss, we generally consider that single order, means or not order, that which moment we are considering, whether the first, second or third, we are just considering in this way. But when we are considering more than one random variable, in this case we are taking the bivariate case first. So, the that when we are describing some joint moments, so we have to describe that both of them. So, for x it is rth, for y it is sth. So, this joint moment of the random variable x and y. So, the order of this r and s is respectively for the first and the second random variable. So, this is the way we describe this joint moment. And so, when we are calling that it is r sth joint moment, that means we are considering the expectation with respect to the origin, that is why it is x power r and y power s. So, as these are the discrete case, that is why we are taking the summation for all possible x as well as all possible y, x power r and y power s multiplied by their probability mass function, joint probability mass function pxy xy. And for this case, when we want to know what is the order of this joint moment, this order of this joint moment is declared as to be the r plus s. So, what is the total of this r and s, that is the order of this joint moment. So, if we just now want to take that expectation of x y, that is both the r equals to 1 and s equals to 1, then it is that summation for all possible x and y. Basically, this is double summation in the sense that two random variables are there, but here it is both are written in the same, all x and y, x multiplied by y multiplied by their joint mass function. And so, this expectation of x y is a second order moment, because this is x is the r is equals to 1 and s is equals to 1 here. So, this is a second order moment. Similarly, if we consider the continuous case, then instead of that summation we have to do the integration over the entire support of the random variables. So, the joint r sth order r sth joint moment of the not order, this will be joint moment of the random variable x and y is given by their expectation of x power r and y power s, is the integration from minus infinity to plus infinity for both x and y, x power r y power s multiplied by their joint probability density function, which is f x y x y. So, this will give that joint moment of order r plus s again. So, now if we just see that the joint first order moment, if I just want to see the first order moments means one R or S, either one of these two will be 1 and other one should be 0. So, make it the first order moment. So, the first order moment, how it comes, if we just see for this x and y. So, that if we consider that m1 0, that is R equals to 1 and your S equals to 0, that means we are taking only x, y power 0. So, expectation of x. So, this will be obviously we will go to that mu x, we know that this expectation of x is mu x. So, the in between steps that you know, that just simply following that general equation, that is x power r. So, here x power 1 and y power 0, which is 1. So, then this joint density dy dx. Now, you see when the first integration we are taking with respect to the dy. So, that means the x we can take out from this integration, and if we just take this integration from minus infinity to plus infinity, that means the entire support of y of this joint distribution, then you know from our previous lecture that this is nothing but the marginal density of x, because over the entire support of the y, that y is taken out. So, we are doing the integration with respect to the y. So, it is marginal out, we can say. So, what is remaining is that marginal density of the x. So, now, this integration, the first one with respect to y, yields that it is the marginal density of x. So, f x x. Now, if we take this integration, you know, this is just now we have discussed, this is nothing but the expectation of x, which is that mu x. So, the first order moment when we take that r equals to 1 and s equals to 0, which is yielding to be that mean of the one random variable x. Similarly, if we just take the other one, that is r equals to 0 and s equals to 1, that means we are taking the expectation of y, which is obviously yield that mu y, that is the mean of the random variable y, which is shown here, that is m01 expectation of y, which is equals to mu y. Now, if we go for the second order moments, now second order moments, there are three different cases can happen. One is that r equals to 2 and s equals to 0, or r equals to 1, s equals to 1, or r equals to 0 and s equals to 2. So, both the cases, as long as the summation is equals to 2. So, these are all second order joint second order moment. So, this m20 is it is expectation of x square. This is a second moment with respect to the origin. m11, that means r equals to 1 and s equals to 1, which is your expectation of x y, this one, and this m02 is expectation of y square, second moment with respect to the origin of the random variable y. Now, joint r-th order central moment of the random variable x and y. When we are talking that central moment with respect to that random variable x y, that means we are taking the moments with respect to their respective mean. So, respective mean here for the for x it is mu x and for y it is mu y. So, that we have to consider we are basically shifting the that origin to that the coordinate mu x comma mu y. So, with respect to that the point mu x comma mu y, we are taking that moment. So, as we are calling that RSF moment, r comma s, this joint central moment, then that means the x minus mu x power r and y minus mu y power s. And as you know that these are the functions of those random variables, simply you have to replace that x minus mu x power r and y minus mu y power s multiplied by their joint probability density, and take the integration from over the entire support of the random variable x. So, maybe you can see here that for the continuous case we have discussed some more of this central moment as well as the different order of this moment, and for the discrete case we have just started with the what is the general expression of the moment. So, whatever we discuss for both that continuous and the discrete, both are applicable for both the types of this random variable. Only thing that as for the discrete case it is the probability mass function, we can go for the summation, and here for the continuous case we are just going for the integration for the entire support. So, just this is the difference, otherwise both the equations, all the equations that we have discussed is applicable for both the cases. So, next if we just want to increase the number of random variable we have considered, here if we just want to extend it to that to the n numbers of random variables. So, here if it is a discrete case, okay, so far as our notation is concerned, this thing should be capital, that is the random variable x1. So, capital X1, capital X2 up to capital Xn. So, there are n random variables are concerned, and for all the random variables we are just considering that power k, that is that kth, you can just say the k comma k comma k up to n numbers of kth order moment for the n numbers of random variables. If it is a discrete case, then we have to do the summation for all xi's. So, they are x1 power k, x2 power k up to in this way up to that xn power k. This is multiplied with their joint probability mass function of x1, x2, xn. So, here this is the random variable x1. So, this will be the capital. So, if you do this one, then that means the same concept is extended for the n numbers of random variables, where all are discrete random variables, and we are getting that this kth order for all the random variables, kth order joint moment is expressed by this, so far as the random variables are discrete. Similarly, if the random variables are continuous, then instead of the summation we have to consider the integration over the entire support for all the random variables from x1 to xn, their power, all power are k, and they multiplied with their joint density. Now, this x would be capital, as you know that this is the notation for the random variable is the capital X. One thing can be mentioned here, it is not necessary that all the power will be k, it can have the different powers. So, different when we are talking about the that power, that means that which moment we are considering. So, for x1 we can consider some order, for x2 we can consider some other. It is not necessary that all these powers should be same. So, in that way we can make the expression more general at the cost of the computational difficulties. So, now if we come back to our that bivariate case again, and we will see that some more properties, how these are related with the whether some basic notation that we have explained earlier. For example, that if the x and y are statistically independent. So, this statistically independent we have discussed in the earlier lecture, that when we can say that there so that occurrence of one does not have any influence on the occurrence of the other random variable. So, and that can be verified through the fact that their joint density is equal to the multiplication of their marginal density. So, that f x y is equals to f x and f y. So, the joint is the product of their marginals. So, if that case is satisfied, then those are called the statistically independent random variable, and it's in such cases. So, that this joint moment, that is expectation of x y, can be shown to be equal to their multiplication of their individual mean, that is expectation of x multiplied by expectation of y. Now, as you know that when we are writing that f x y, basically before I write this one, there are some steps. You know that this is basically that x y multiplied by just now the expression that I have shown, that x y multiplied by that joint density is this. This is for the discrete one, and is simply we have to just put that integration sign as we are considering the continuous one. So, here also maybe that r equals to 1 and s equals to 1, if you put, then x y multiplied by their joint density. So, now as we are telling that this joint, they are statistically independent, that means that joint density is the product of their marginal density. So, we are separating out that x multiplied by the marginal of x and y multiplied by the marginal of y. So, if I do that one, then we are coming to this form, that is x marginal of x multiplied by y its marginal of y dx dy. Now, we can separate out this integration, because this is entirely for this variable x and this is entirely for the variable y. So, we can separate out and do this integration separately, and this one you know that this is nothing but the expectation of x and this is nothing but the expectation of y. So, if they are statistically independent, with this condition, expectation of x y is equals to expectation of x multiplied by expectation of y. Next, one important concept that we will discuss is the covariance. The covariance is the measure of the joint variation. So, how both the random variables vary with each other. That means, if I linguistically if I explain that whether if one random variable increases, what is the condition of the random variable, the other random variable. So, the covariance of two random variables x and y is defined as the expectation of the product between the respective deviations from their mean. So, respective deviations from their mean, when we are talking about, that means we are considering that x minus mu x. So, there is a mean of that x and y minus mu y, mean of the y. So, this is basically the central second order moment when we are considering that for the x minus mu x, this power r. So, this r is equals to 1 and s is equals to 1. So, this expectation is known as the covariance between x and y. So, the expectation is with respect to the joint distribution of this x and y. Now, if we expand this one, this expression, we have already seen that how we can expand this expression. Then there are two things can come out, that is, for any random variable, if we just take that x and y, then we can show that the covariance between x and y is equals to the expectation of x y minus mu x mu y. So, basically if we just take this expression and if we come through their respective expansion of this variable, that is this one, that is taking that r equals to 1 and s equals to 1, and then if we take if we expand this one, and then we can show that this one is equals to this expectation is equals to their joint expectation, that is expectation of x y minus the product of the mean of the x and product of mean of the x and mean of y. So, this is what is shown here, that is covariance of x and y is equals to expectation of x y minus mu x into mu y. If this x and y are statistically independent random variable, then this covariance is equals to 0, and this rho x y, this is a correlation coefficient, we will come to this one in a minute. This will also, we can show that this is also 0. So, before that, if they are statistically independent, if we say, then just now we have seen that this expectation of x y is equals to expectation of x multiplied by expectation of y. This is what we have seen just now, if they are statistically independent. So, this is now your mu x and this is mu y. So, if we put this one in this form, so for the statistically independent random variable x and y, so this one is becoming 0. So, that is why the covariance between two random variable, if they are statistically independent, then the covariance equals to 0. Now, up to this point, whatever we have discussed, we have got three important information, and we will see some problems on this. These informations are, if we can state that the joint density of two random variable is the product of their individual marginals, then those two random variables are independent. Now, if the random variables are independent, then their covariance is equals to 0. So, we can take up some problems where if we just show that their marginal densities the product of their marginal density is equal to their joint density, and then from the joint density if we want to calculate the covariance, then that covariance should come equal to 0. So, we have generated some this type of some problem, and we will just discuss after this discussion, when we will just start with that assumption that this is independent, and we will just show also that whether they are really the product of their marginals are equal to their joint distribution or not, and after that from the joint distribution we will calculate the covariance, and we will see that whether that covariance is coming to 0 or not. So, these properties will be cross checked through those problems. So, after this one thing is also important after saying all these things, but the converse is not true. The converse is not true means that if sometime we see that the covariance is 0, but that does not indicate that those are statistically independent. So, if we recall our earlier lecture, that we told that the two random variables are statistically independent if and only if the condition that their joint is equal to the multiplication is the product of their individual marginals. So, from that one we are starting and we are ending up to the condition that if they are independent, then the covariance will be equals to 0. But if I somehow show that okay, their covariance is equals to 0, we cannot say that the reverse is true, that is that they are independent. We cannot say that one. This also will be showing in terms of some pictorial view in after few slides. Now, some more equations. These equations we also discussed earlier with respect to the single random variables. Now, as the number of random variables are more than one in these multiple random variables, so we will also see these properties as well, that if x and y are any two random variables and a and b are any two constants, then expectation of ax plus by is equals to a mu x plus b mu y. Recall that in the earlier lecture in with respect to the single random variable, we have shown that expectation of Ex is equals to a mu x, that is whatever the constant is multiplied with the random variables, it can be taken out from this expectation operator, and so that it will remain as this expectation of x, which is nothing but mu x. So, this is now additive also if there are more than one random variable and they are added to each other with some other constant. So, this can be again applicable, and we can just write that expectation of ax plus by equals to a expectation of x, which is mu x, and b expectation of y, which is mu y. Earlier in the context of the single random variable, when we are considering the variance, then also we have seen that whatever the constant that is multiplied, when we are taking out of this variance operator, those will be in terms of the square. We can take it out and then the variance of the random variable. But when we are considering more than one random variable, then the new term, that is a covariance, also will come into the expression. That is, the variance of the sum of two random variables is given by the sum of terms representing the variance of each of the variable and a third term representing their covariance. So, variance of ax plus by when we are taking, so a can be taken out of this variance operator, so that it will be a square. So, a square sigma x, which is the variance of x, plus similarly for the second one, the b square multiplied with the variance of y, which is sigma y, plus another term will come, which is 2ab multiplied by the covariance between x and y. So, this is the full expression when the covariance is considered. So, easily we can just draw one more step, that if the random variables are independent, then we have just now we have seen the covariance will be equals to 0. So, in that cases the variance of ax plus by will be equal to a square sigma x plus b square sigma y, no third term, because the covariance will be 0 in case of the independent random variables. Okay, this is what is explained here also again, that if the x, y are independent random variables, then the variance of ax plus by equals to a square sigma x plus b square sigma y, because the covariance between the x and y is equals to 0. Now, from the equation, that whatever the expression of this covariance what we have seen, it can be noted that this covariance xy is large and positive when x and y tend to be both large or both small with respect to their means. Similarly, in contrast to this, if one variable is large and the other one tends to be more, and vice versa, of course, the covariance is large and negative. And if there is no relationship between two random variables, instead of no relationship, we can say that if they are independent, then the covariance does not exist. So, using this one, if we now when we are talking that this large and positive and large and negative, if we just want to make it standardized, then we can have some base over which we can just conclude the or some we can quantify the nature of their association. Now, to standardize this, we are using their individual standard deviation. This is how we will show that thus the covariance x y is a measure of their linear interrelationship between x and y. The coefficient of linear correlation, that is rho, that is correlation coefficient rho, is normalized covariance between two random variables x and y. Now, how this normalization is done is this, that rho x y, that is the correlation coefficient between x and y, is equals to covariance between x and y divided by product of their standard deviation, which is square root of sigma x square sigma y square. You know, these are the variance and their positive root is your standard deviation. So, product of their standard deviation. So, this is the normalizing factor. If we normalize this, then this total quantity is the correlation coefficient. Now, why we have used this one for the normalizing constant is that this covariance xy is having a maximum upper limit is equals to their product of their individual the square root of their variance, product of their variance. Now, if this is the maximum limit of this one, this will also show in terms of some inequality theorem. So, if this is the maximum one, then you can say that, so this total quantity can go up to the maximum of the plus 1. Obviously, there will be, we have to take the square root of this total term, so that it will, we can also show that it is a limit of this quantity is basically from the minus 1 to plus 1. And if they are independent to each other, then we know that this covariance is 0. So, this correlation coefficient also will be 0. So, that is what actually was mentioned in this one, as I told that we will discuss in a minute, that if this covariance is 0, then this rho x y, that is correlation coefficient between these two, are also equals to 0, which is now clear from this expression, that if covariance is 0, then this correlation coefficient between x and y is also equals to 0. Now, as I was telling that this correlation coefficient is range between 0 and range between minus 1 to plus 1. So, this rho x y is from minus 1 to plus 1. So, this plus 1 basically indicates that there is a positive dependence and a perfect linear relationship. If it is exactly equal to 1, perfect positive relationship, and if it is equals to the minus 1, then it is perfect negative linear relationship. That means, one increase of 1 is ensures that the decrease of the other one. Similarly, for the plus 1, increase of 1 ensures that the increase of other one also. Now, to prove this one, there is a inequality, that is Cauchy-Schwarz inequality. It states that for the vectors x and y of an inner product space, that if we take this inner product their mod and square, which is less than equal to their individual inner product. Now, using this one, if we just fit it into that expression of the that expectation of their covariance with the central moment, you know that this one we described earlier, this is the covariance with respect to their that is central second order moment taking r equals to 1 and s equals to 1, that is x minus mu x, y minus mu y multiplied by their joint density and integrate it over the entire support of the random variable x and y. Now, if we take this one as a square, now which is your so that x minus mu x square, one this joint density multiplied by their this the other one, that is y minus mu y square fx, that the one density, because there is square. So, one we are taking here and other one we are taking here. So, this one if we just take this in integration, so this is satisfied with this inequality. So, maximum of this quantity should be the product of this one multiplied by the product of the product of this and this. So, as this is the maximum upper limit, now if we just see what are these two are individually means, that is x minus mu x square, their joint density dx dy, which is nothing but if we just first take the, because this is with respect to the x. Now, if we take this first integration from this the entire support of the dy, and so then with respect to the y, this can be taken out from this integration. So, what is remaining within this integration is that minus infinity to plus infinity their joint density with respect to y. That means, we are marginal, the y is marginal out, what is left is that marginal density of x. So, that is why this marginal density of x multiplied by this x minus mu x square, and you know this expression is nothing but the variance of x, and which is the central moment, that is with respect to the mean, the second order moment of the random variable x only. So, this is sigma x square. Similarly, the other one is equals to the sigma y square. Now, if we just put this one in that expression, that is the expression of this one what we started with, this one. So, this is your that covariance, the covariance square is less than equals to, this is your that sigma x square and this is your sigma y square. Now, this is here is shown here, the covariance square less than equals to sigma x square sigma y square, which is now if we just take this one out, this one to the left side, then this will become as a rho xy square. So, rho xy square, because we have just now we have seen that rho xy is the covariance of xy divided by square root of sigma x square sigma y square. So, this is your correlation coefficient square, which is less than equals to 1. This is verifying that this correlation coefficient should be between -1 to +1. Now, if we say that what does these things means, that when this when it is exactly equal to the +1 or -1. So, when it is equals to exactly equals to the +1, that means there is a perfect linear relationship, and which ensures that the increase of one random variable ensures the increase of the other one, and also the opposite, when it is exactly equals to the -1, then the increase of one is ensuring that decrease of the other one, and vice versa. So, these are all on a perfect straight line. As long as these are on the perfect straight line, if it is having a decreasing trend towards the positive x, then this is -1, and otherwise it is +1. Now, in between, if we just see, if we see this kind of relationship, that is, this is the x, this is the variable x and this is variable y, where we have not seen any kind of trend. So, there it is a we can get a exactly equal to or very close to 0, the correlation coefficient will be very close to 0 or exactly equal to 0. Now, in between this one, so this type of relationship we can say that this is having a positive relationship. So, this will be the rho will be equals to between 0 and 1, and for this case, as we have the way we have generated, this correlation coefficient is coming around 0.92 or so. So, this type of so this is also a positive relationship. The increase of 1 is ensuring the increase of the other 1, and the correlation coefficient R is equal to approximately equal to 0.92. So, here you can see that this axis limit. So, this is that for the x it is generally varying between 0 to say 1, and for y it is varying between 8 to 11 kind of thing. So, this range does not have anything to say that how their relationship will be. Only thing that what we are saying that what is their linear dependence or linear association between two variables, which is reflected through the correlation coefficient. So, however, one thing is also important here to note that from the figures that we have shown below, we can see that when the relation between x and y is non-linear. For example, we are talking about a semicircular shape, that is there is a, so x and y are related through the equation of this circle. So, which is a nonlinear equation. Here there is a relationship with the sine curve. So, there are the relationship between the x and y is perfect, but need not be linear. So, as long as the relationship is not linear, so this rho is equals to 0. This can be mathematically this also can be proved even for the expression, for example, that x equals to y square. So, which is a perfect relationship. So, the first order, the quadratic relationship. But if we calculate their correlation coefficient between x and y, x and x square say, then also it will become 0. So, this is basically a point of caution that that correlation coefficient should not, if it comes near 0, that should not be concluded that there is these are independent, which actually we are trying to mention when we are telling that the reverse is not true. When the covariance between two variables are 0, that does not mean that they are independent. This is what is reflected here, because the so why we will get here is 0 is that the correlation coefficient is the measure of the linear dependence, the linear association. So, linear here is important. As long as the relationship is linear, or how much linear relationship is there we can get some correlation coefficient, but for the nonlinear relationship this is equals to 0. So, the significance of this correlation coefficient, although the rho is a measure of the degree of linear relationship between two variables, it does not imply that a causal effect between the variables. This is one thing which is also important to note, that the correlation and causality should not be mixed up, because a positive correlation coefficient also is not a indication that the one variable is having some causal effect on the other one. So, but however, in many applications, particularly in the civil engineering application, we to identify some what is the causal factors, we use various statistical measures among which the correlation coefficient is one of the most important out of them. But these things should be kept in mind, that even though you get some very significant correlation coefficient, that may not always indicate that there is a causal relationship. So, that is what is mentioned here, that although the rho is a measure of degree of linear relationship between two variables, it does not imply a causal effect between the variables. The two variables x and y may both depend on the another variable. So, this is one special case that we are giving as an example, but not the only case where this type of relationship may occur. Only one special case we are just mentioning here, that two variables x and y may both depend on the another variable. So, in which case there will be a strong correlation between the values x and y, but the values of one variable may not have the direct effect on the values of the other. So, even though we are getting we may get a strong correlation coefficient, that doesn't indicate that they are having any causal effect on each other. We'll take one example, particularly that I was discussing, that when we say that they are independent and their covariance should be equals to 0. So, that type of one example is taken here. This is a structural engineering problem. If the one structure is made up of two structural element, and failure or the lifetime of the each member is, we can say that this is exponentially distributed depending on their quality of the material, and both can have the exponential distribution and both can be independent to each other. In such cases, one such problem is taken here. So, the life of the structure consists of two members depends on their individual lifetime x and y. So, here the random variables which are considered is the x and y is the individual lifetime of the two members of a structure, and both the x and y are exponentially distributed, and their joint density function, that is x and y, is given as f x y is equals to their product of their marginal distribution, and the marginal distribution of x, that is the first random variable, is that e power minus x, and second one is the 2 e power minus 2x. So, you can say that both are exponentially distributed. F x is that e power minus x, and other one is 2 e power minus y. So, and we are taking their multiplication, that means that x and y are independent to each other, or I should say it is the other way. As they are independent, we are assuming they are independent, that is why we are getting their joint density is equals to the product of their marginals. So, that e power minus x multiplied by 2 e power minus 2 y, which is giving you this this expression as their joint density, which is equals to that x and y, the limit of this x and y should be from 0 to infinity for both x and y. One thing is also important here when we are taking this type of relationship. We are supposed to basically, okay, fine, let me finish this one. So, we have to determine the covariance between x and y. So, when we are interested to know their covariance of x and y, if it is not this type of known distribution, that is exponential distribution is known to us and we know their properties, and by this time in the earlier lectures also we have described different standard distribution for which we know the different properties. So, here the exponential distribution which is having a form of this lambda e power minus lambda x, and you know that for their mean is 1 by lambda. So, otherwise what could happen if the joint distribution is given for some other problem? We are supposed to obtain their marginal distribution. From the marginal distribution we are supposed to get their mean, and after that we can use that one in the equation of the covariance. That type of example also we will take up after this, but as in this particular case it is the exponential distribution, and we know there what are the properties. At least the first moment we know that it's the mean is 1 by lambda. So, we know what is the mean of x and we know what is the mean of y. So, here, so you can see that as this is that exponential distribution is e power x. So, the mean of the x is equals to 1 and mean of the y equals to 0.5, that is 1 by 2. So, these two information is already known to us. Only thing we have to calculate their covariance, that is the expression of Ex we have to calculate, and from there we can calculate their covariance. So, we have to first get that this is the only unknown that we have to determine the expectation of x, y. So, which we know that this is from the over the entire support that x, y multiplied by their joint density, which is equals to here from 0 to infinity, these are the support of this x and y, and we have to do this integration. So, after doing this few steps for this integration, we see that this expectation of x y is equals to half, that is 1 by 2. Now, if we take this one in the expression of this covariance, that is covariance of x comma y, that is expression of x y minus mu x mu y. Now, we already know what is mu x and we already know what is mu y. So, this is equals to half minus 1 multiplied by 0.5, which is equals to 0. So, this answer basically was expected, because we started with that thing that these are independent. So, as they are independent, their covariance would be equals to 0. That is why we can note here that this confirms that there is no covariance between two random variables which are independent. We will take up other problems similar, but for those cases we do not know what is their individual mean. So, we have to calculate their mean as well as their joint moment, that is x y. We have to calculate, and there we can see that what their covariance is. So, the joint density of two random variables x and y is given by this f x y is equals to 1 by 9 x, and the support is that from 0 to 3 and y is from 0 to 2. So, two different range of this support. This is the joint PDF form. There is only one variable x. So, you know that when we are declaring that one joint density is there, we are ensuring that this is a valid PDF, joint pair PDF, and you know how to verify that. We have discussed earlier, that is integration over the entire support of the random variables should be equals to 1, and this should be greater than equal to 0 for the entire support. So, which both the things are satisfied. So, what we have to do here in this problem, that we have to determine the covariance between x and y. Now, to do that one, we do not know their marginals and we do not know their mean. So, we have to obtain that one first. So, in order to determine the covariance, we have to compute the expected values of the x y, x and y, all three. So, expected value of this x y is equals to their entire support from this minus infinity to plus infinity x y f x y from 2 to from 0 to 2 and from 0 to 3, it is x y dot 1 by. So, this is your that joint density. So, if we do this one this integration after few steps, you can check that this expectation of x y is becoming equals to 2. Now, similarly, we have to get that expectation of x as well as we have to get the expectation of y, and from there we can get what are these things. So, you know the expectation of x is equals to their x multiplied by the joint density of dx dy. So, this is the entire range, and if we do this integration with respect to the that x and then y, then we will get that this range, which is we will get ultimately we will get that is equals to 2. So, expectation of x is equals to 2. Similarly, if we take that expectation of y, which we do following the same expression, we will get the expectation of y is equals to 1. So, we got expectation of x, expectation of y and expectation of x y. So, the covariance is equals to, you know that expectation of x y minus expectation of x into y, which is equals to 0. Now, this is interesting. So, we started with the problem where we have seen that the covariance is becoming to be equals to 0. So, this indicate, or this may indicate, I should not say that this this indicate that the covariance, this simply indicate the covariance between the x and y equals to 0. This may be a result of that this either that x and y might be independent. If they are independent, obviously the covariance will become 0. But we cannot ensure from this result that they are independent, because we have got that covariance equals to 0. So, covariance equals to 0 is not the proof to declare that this x and y are equals to 0. But for our curiosity sake, we can just check whether really the x and y are independent, and that is why we got the covariance equals to 0 or not. So, for that what we have to do, we are having that joint density with us. Now, we can get their individual marginals, and if we get their individual marginals, after that we can do one check whether they are independent or not. So, our marginal density what is given here is this, that is 1 by 9 x for this range. So, we can get their marginals 1 of marginal of x and marginal of y, and we can multiply these two marginal and we can see whether this is coming equal to this or not. If it is so, then they are independent, we got the covariance equals to 0. If it does not come also, that does not mean that it will always come, as I was telling. So, you can just take up is as your cross check, you can just check it once yourself to see that why the covariance has come to 0 for this particular problem. So, there are other properties as we are starting this class for this multiple random variable, and those properties we will take up in the next lecture. Thank you.